So now we're going to talk about using sinusoidal or periodic functions to model periodic phenomena, things that repeat themselves, but we're not going to use angles. So here's an example here of the cosine function and sine function. Obviously theta, we're moving through some angles here, which we've done lots of, but we want to try some applications on this. Not our horizontal axis in the real life isn't very often an angle. It's time or distance or hours worked at no frills or whatever. So we don't see angles a lot in real life. So we're going to move this into a more interesting application. So I want to start with writing a model for a Ferris wheel. I think everyone's been on a Ferris wheel before or seen a Ferris wheel, so they have a sense. It's a nice example of something repeating itself in terms of the motion. So really we're going to try to visualize this structure here, this Ferris wheel here on the left, as simply an object moving around in a circle. We're going to focus on the height. See how this dot here is moving up and down the y-axis? It's the height that we're going to care about. And here's the wave that obviously gets created over here from measuring that height. So just to line it up a little bit closer, what we're going to do is, the maximum value is going to be here. The minimum value is going to grab there. The midline is going to sit in there. We're going to try to attach them in that way, which is going to help us. So just say for simplicity, we'll talk about a Ferris wheel. Now this is I know it's a roller coaster, but I thought it was kind of cool. So for simplicity, we're going to get on the top of a Ferris wheel. I know we can't in reality, but just to keep our calculations simple for now, we're going to do this. So here's a Ferris wheel rotating around, and we have to be told how long it takes to spin around. So let's say it takes 8 seconds for one spin. That's the period. We need to know the radius of the Ferris wheel, which is, in this case would be 5. And we need to know how far off the bottom is. This would be 1 meter. Obviously, the Ferris wheel can't plow through the ground. We can't have an x-axis in our circle plowing through the ground. So we always have this, we're always going to have some kind of lift to bring the circle off of the ground somehow, for the Ferris wheel example. So I know my radius here is 5. I'm just going to build a quick graph here on the right. So if my radius is 5 and I'm 1 meter off the ground, I know my midline has to be 6. 5 plus 1 is 6. And then at 6, if I have to go up 5, I hit 11. And of course, down 5, I hit 1. So there's my 1 meter off the ground. And it was, 8 seconds. So it's 8 seconds to go all the way over. Here's my maximum value. Here's my minimum value. And I have the graph. So again, we're going to hop on the top of the Ferris wheel. It's going to slide. You're going to rotate down. And you're going to head back up. 8 seconds later, you're sitting back up at the top. That's what it would look like. If I'm going to write a model for this, which I can, I know my A is 5, my amplitude, my vertical stretch. There is no displacement. I'm going to use a cosine model, and that's why we chose to hop on the top, because cosine starts at a peak. So let's suppose I can just, I can't, but suppose I could hop on at the top here. Cosine starts at a peak, so there's no need for a vertical or horizontal shift. The period I know is 8, and the vertical displacement is 6. So this is what the function is going to look like, the model. So this is the basic function, y equals whatever, cos theta, but it has these distortions or these transformations on it. So here's the A out front, as always. Here's my horizontal shift. I'm going to write the period down like this and plus c. Now I know before we had a k, right? We had y equals k theta, and that k told me the number of cycles and so on. We dealt with that, and that's fine, and that works. But I think this is a way easier way to write this. I'm just going to replace k, because I know k is 360 over the period. So I'm just going to replace that k here in my equation, my function cos, with 360 over the period, and there's my theta there. That's what this is here. So this 360, this is up, so divided by the period is this replacement I'm doing with k. And the reason why I'm doing that is because with these applications with Ferris wheels, we're told the period all the time. We're not told k. We don't see any questions. We look at a Ferris wheel, we don't say, oh, well, k is obviously whatever. We look at it and say, oh, well, the period is obviously whatever. We can look at it and just see how long it takes to go through a cycle. So it's way easier to have the variable period here exposed as opposed to having a k sitting there for us. So this is a better structure for us. So this is the structure we're going to use. Of course, 360 are in degrees, obviously. So to plug in our values, A was 5. There's no horizontal displacement, so it's just 0. I mean, you can drop that and just put T. Okay, 8 was a period and 6 was the vertical displacement. So just to confirm our formula, I'm just going to try 1 second and see what it looks like. So if I go back to our question, this is 8, halfway down here is obviously 4, halfway through the halfway would be 2, 1 second is right around here. So I'm going to plug in 1 second to our equation, and we should get something, if we do it right, we should get something in this range, up there, like whatever, 10 or who knows, something. So 1 second, it won't be 11, 1 second would hit there. Sorry. Sorry, okay. So 1 second would hit 10, right about there. So let's try 1 second. So trying 1 second, I'm going to plug it in. There's my 1. Everything stays the same. Obviously, t minus 0 is just 1, so it stays there. Okay. Now, this part's really interesting for us. This is actually a really key spot for us. So this 360 divided by 8, because it's just a 1 anyway, right? So 360 divided by 8 is 45. So now I have cos 45. Now, this part's important. Now, this is how we're linking our calculator to our Ferris wheel, because remember, our calculator has been loaded in with all the trig functions, all the trig values, but it doesn't know we're talking about a Ferris wheel. So how do we get our calculator to understand where we are? And that's what this little section is doing here. So 1 second is 1/8 of the way through the ride, right? Now 360 divided by 8 is 45. And 45 is actually 1/8 of the way around the unit circle. So that's what's happening. So let's take a look at this here a second. So here's my 1 second. Here's my 8 seconds. The whole thing is 8. Here I am sitting at 1. So I'm at 1/8 of my way through the cycle. So I need my calculator to kick out the value it has loaded in it 1/8 of the way through. Okay. To do that, this little reduction, 360 divided by 8, gives me 45. And I know if I think of a unit circle like this, and I'm at 45 degrees right here, right? There's 45, that's 1, that's 2, like 2 45s, right? 1/8, 2, 3, 4, 5, 6, 7, 8, right? That spot there, 45 degrees, is 1/8 of my way around the unit circle. Just like 1 second is 1/8 of my way through this cycle. So it's linking it together. So this is the correct value. So the value that the calculator kicks out is going to be the proper value, 1/8 of the way through the cycle. So that's what cos 45 is hitting for us, which is good. So that part's really, really interesting, I find. So it's important to see. So on our calculator, of course, we know, exact ratio, of course, we know 0.707. So the calculator kicks out 0.707. So the calculator thinks, okay, we're just sitting at 0.707. I guess that would be the height, 0.707, which is obviously wrong. The height of the rider isn't 0.707. So now we have these two other manipulations that just come from our model. Okay, the 5 and the 6 just adjust the trig value to fit our Ferris wheel. So our function says, okay, take this, this theoretical 707 height from the calculator that will work on just the general theoretical case, multiply it by 5 because the Ferris wheel has an amplitude of 5, and add 6 to that because the Ferris wheel has a midline of 6, right? Remember, the basic case doesn't have an amplitude or a midline. This one does. So I take my 707, multiply it by 5, and then I add 6, and I get 9.5. And if I go back and check the graph, right, at 1 second, here's my 1 second here, right? Remember, that was 4. I'm at 9.5. I think I said 10 before, but yeah, around 9.5. So that's it. So it's kind of close. So it gives us the exact value. It actually works. It gives us the proper spot. Okay, so like I said, that's why I really like having that 360 over the period in our expression, because it shows us perfectly how we're linking not just Ferris wheels, any periodic function into our calculator. Now, let's just do this one more time here, just quickly. So for a normal Ferris wheel, of course, we're going to get on at the bottom. So we can't just fly through the air and land on the top here. So we're going to build a model, for getting on at the bottom. So it's going to be the same thing here. We'll have 8 seconds for our spin. The radius will be 5, and we'll get on still 1 meter off the ground. So that's all going to be the same. So nothing new there. However, we're going to get on at the bottom now, and we're going to ride up, get to the top, and then head over to the bottom here in our 8 seconds. So everything else can be the same, right? 6 is the midline, 11 is the peak, and 1 is the trough. And we're in 8 seconds. So I'm going to use the cosine function again, and you can use the sine if you want. I'm just going to use the cosine because I like aiming for that peak there. So the midline here is going to be 6. So our function, this is basically it here, the general a, a, d, and period, and so on. Our midline is 6, which is the same. The amplitude we know is 5, which is the radius of the circle, which is exactly the same. Now this is the interesting part. So the horizontal shift. Now I'm using a cosine function. So the cosine function starts at peak here, but my function, my Ferris wheel, isn't over at a peak. I'm 4 seconds down. So I have to draw that peak back over to the actual starting spot of my cosine function, again, so it matches my calculator. Remember, the calculator has cosine starting here and dropping down. It doesn't have it floating over in space here. It's starting on the y-axis. So I have to draw that curve essentially over to the y-axis like that. And we just look at our scale, and that was just a draw of 4 seconds, 4 units. So that just means I have to have a t minus 4. That's just my horizontal shifting. That's all that happens. Now, same thing. So that's going to be my formula. That's it. So I'm going to try 1 second again and see what I get. If this is 4 seconds there, 2 is there, 1 is there. So if I have 1, I should get some kind of height bigger than 1, whatever, maybe somewhere 2 to 3. That should be the value. I'm going to plug in my 1 second here. There's my function. There's my 1. Everything's the same, right? The 5, 8, the 6. There's my 1. 1 take away 4. It's easy. That's negative 3. So let's take a look at what's happening here. Okay, so I have 360 over 8. That's going to be my 45. And then I'm multiplying it by negative 3 in this case. So let's try this. So there's my 45 part is easy. Now I have to multiply it by negative 3. So 45 times negative 3 is negative 135. Now let's just make sure this is making sense. Now let's take a look at this. 1 second, my actual Ferris wheel question, 1 second is 3/4 of my rotation left of the peak. So let's look back here at my graph here. You see, here's my peak, 4, and I'm over here at 1 second. So there's my 2, right? And there's my 3. So I've gone, if I break this up in the quarters, I'm 3/4 left of my peak here, okay? If I go back into, well, what's negative 135? If I think of my unit circle, if I go negative 135, that's 3/4. That's negative 45, negative 45, negative 45. I have these 3 negative 45 values to give me my 135. That's, 3/4 left. I've gone left of my starting value. That's making this match my calculator perfectly again. And now every time you do this, you don't have to sketch this out. I just want to show you how it's working. From now on, you can just move through it in your calculator. That's fine. So again, this is negative 0.707. That's the theoretical calculator version. I have to adjust it with my 5 and my 6 because I'm talking about a Ferris wheel, and I get just around 2.47 meters. And we said 1 second is there. Yeah, that's 1. If that's 6, halfway is 3. I'm around 2.5, which works. Okay, so hopefully that made sense. And what I want you to do is there's a posted assignment called the Ferris wheel assignment. I want you to complete that and submit it. Great.